An Elementary Course in Synthetic Projective Geometry by Derek Norman Lehmer. Chapter 3, Combination of Two Projectively Related Fundamental Forms. Section 47, Superposed Fundamental Forms, Self-Corresponding Elements. Section 48, Special Case. Section 49, Fundamental Theorem, Postulate of Continuity. Section 50, Extension of theorems to pencils of rays and planes. Section 51. Projective point rows having a self-corresponding point. Section 52. Point rows in perspective position. Section 53. Pencils in perspective position. Section 54. Axial pencils in perspective position. Section 47. Superposed fundamental forms, self-corresponding elements. We have seen, section 37, that two projective point rows may be superposed upon the same straight line. This happens, for example, when two pencils, which are projective to each other, are cut across by a straight line. It is also possible for two projective pencils to have the same center. This happens, for example, when two projective point rows are projected to the same point. Similarly, two projective axial pencils may have the same axis. We examine now the possibility of two forms related in this way having an element or elements that correspond to themselves. We have seen, indeed, that if B and D are harmonic conjugates with respect to A and C, then the point row described by B is projective to the point row described by D, and that A and C are self-corresponding points. Consider more generally the case of two pencils perspective to each other with axis of perspectivity U', figure 9, cut across them by a line U. We get thus two projective point rows superposed on the same line U, and a moment's reflection serves to show that the point N of intersection U and U' corresponds to itself in the two point rows. Also, the point M, where U intersects the line joining the centers of the two pencils, is seen to correspond to itself. It is thus possible for two projective point rows superposed upon the same line to have two self-corresponding points. Clearly, M and N may fall together if the line joining the centers of the pencils happens to pass through the point of intersection of the lines U and U'. Section 48. We may also give an illustration of a case where two superposed projective point rows have no self-corresponding points at all. Thus, we may take two lines revolving about a fixed point S and always making the same angle alpha with each other, figure 10. They will cut out on any line U in the plane two point rows which are easily seen to be projective. For given any four rays SP which are harmonic, the four corresponding rays SP' must also be harmonic, since they make the same angles with each other. Four harmonic points P correspond, therefore, to four harmonic points P'. It is clear, however, that no point P can coincide with its corresponding point P', for in that case the lines PS and P'S would coincide, which is impossible if the angle between them is to be constant. Section 49. Fundamental Theorem, Postulate of Continuity. We have thus shown that two projective point rows, superposed one upon the other, may have 2 points, 1 point or no point at all, corresponding to themselves. We proceed to show that if two projective point rows superposed upon the same straight line have more than two self-corresponding points, they must have an infinite number, and every point corresponds to itself. That is, the two point rows are not essentially distinct. If 3 points A, B, and C are self-corresponding, then the harmonic conjugate D of B with respect to A and C must also correspond to itself. For 4 harmonic points must always correspond to 4 harmonic points. In the same way, the harmonic conjugate of D with respect to B and C must correspond to itself. Combining new points with old in this way, we may obtain as many self-corresponding points as we wish. We show further that every point on the line is the limiting point of a finite or infinite sequence of self-corresponding points. Thus, let a point P lie between A and B. Construct now D, the fourth harmonic of C, with respect to A and B. D may coincide with P, in which case the sequence is closed. Otherwise, P lies in the stretch AD or in the stretch DB. If it lies in the stretch DB, construct the fourth harmonic of C with respect to D and B. This point D' may coincide with P, in which case, as before, the sequence is closed. If P lies in the stretch DD', we construct the fourth harmonic of C with respect to DD', etc. In each step, the region in which P lies is diminished, and the process may be continued until two self-corresponding points are obtained on either side of P and at a distance from it arbitrarily small. We now assume explicitly the fundamental postulate that the correspondence is continuous, that is, that the distance between 2 points in one point row may be made arbitrarily small by sufficiently diminishing the distance between the corresponding points in the other. Suppose now that P is not a self-corresponding point, but corresponds to a point P' at a fixed distance d from P. As noted above, we can find self-corresponding points arbitrarily close to P, and it appears, then, that we can take a point D as close to P as we wish, and yet the distance between the corresponding points D' and P' approaches D as a limit, and not zero, which contradicts the postulate of continuity. Section 50. It follows also that two projective pencils which have the same center may have no more than two self-corresponding rays, unless the pencils are identical. For if we cut across them by a line, we obtain two projective point rows superposed on the same straight line, which may have no more than two self-corresponding points. The same considerations apply to two projective axial pencils which have the same axis. Section 51. Projective point rows having a self-corresponding point in common. Consider now two projective point rows lying on different lines in the same plane. Their common point may or may not be a self-corresponding point. If the 2 point rows are perspectively related, then their common point is evidently a self-corresponding point. The converse is also true, and we have the very important theorem. Section 52. If in two projective point rows the point of intersection corresponds to itself, then the point rows are in perspective position. Let the 2 point rows be U and U', figure 11. Let A and A', B and B' be corresponding points, and let also the point M of intersection of U and U' correspond to itself. Let AA' and BB' meet in the point S. Take S as the center of the two pencils, one perspective to U and the other perspective to U'. In these two pencils, SA coincides with its corresponding ray, SA', SB with its corresponding ray, SB', and SM with its corresponding ray, SM'. The two pencils are thus identical by the preceding theorem, and any ray SD must coincide with its corresponding ray, SD'. Corresponding points of U and U', therefore, all lie on lines through the point S. Section 53. An entirely similar discussion shows that if in two projective pencils the line joining their centers is a self-corresponding ray, then the two pencils are perspectively related. Section 54. A similar theorem may be stated for two axial pencils of which the axes intersect. Very frequent use will be made of these fundamental theorems. An elementary course in synthetic projective geometry. This book was written by Derek Norman Lehmer, Assistant Professor of Mathematics, University of California. It was published by Ginn and Company, Boston, 1917, and is now in the public domain. The text is available for free download at Project Gutenberg, read by Jim Renholt. Programming and illustrations by Jim Renholt, 2020. Corrections and comments are appreciated. Thank you for listening.